These workshops have been going on for about 18 months now. This is the 18th, I think, and they're proved to be incredibly popular. Everybody who comes into the meeting comes in as on mute, and so if you want any questions, please use the Q&A box at the bottom of the screen, and we will relay your questions to the presenter. These workshops are sponsored by Liverpool Chirochem. They help provide, help fund the Zoom licenses and such like, and so we're very grateful for them. This session is 2 hours. After 1 hour, we have a break for about 5 minutes or so to give you a chance just to stretch your legs, and we will have somebody, hopefully from LCC, to just say a few words. And with that, I'd like to hand over to, I'm not sure who's speaking first. Is it you, Albert? Yeah, okay. Well,
yeah,
over to you, and I'm really looking forward to this. I think it's going to be a great session. Thanks very much.
Thanks for having us, Chris. So let me share my screen. So this session will be about CLIFS, kinase structure database, and as a subtitle we have making kinase structures work, because the aim of CLIFS is to actually collect all those beautiful kinase structures we have out there and to collate them in such a way that everybody can extract the data from them and look at them in a more generalized fashion, so we can use it in a broader sense, and to also use this for more in-depth drug design, for example. So just to start off with the outline, I'm Albert Kooijstra. I work at the University of Copenhagen, and I will take care of the first hour of the workshop. So I will go into the website of CLIFS, show you different functionalities, and then at the end I'll quickly show you the description of the different web services that we have and how CLIFS can be used, for example, in the data analytics platform NIME. After this, I'm very happy that Andrea and Dominique are accompanying me here, because they have been amazing in doing kinase research, and in a lot of their efforts they have also been using CLIFS and doing beautiful things, for example with KISM and OpenCat. So then they'll introduce their work, and with a focus on OpenCat and KISM. So this workshop will be quite interactive, so you can follow along on the CLIFS website, and in the second hour Dominique will also show you the links to Jupyter notebooks that you can follow along with interactively. So just to start at the end, I want to thank you for being here and for your attention, and of course I also have to acknowledge everybody who has been involved in the development of CLIFS throughout the years, and especially Chris de Graaf, Oscar van Linden, and George Kanev, who have been pivotal also in establishing the CLIFS database. CLIFS makes use of a lot of different software packages and tools, so we also would like to thank them for developing it and making it available, and also different resources that are collated into the CLIFS database. And of course, I also want to thank the CLIFS users out there, because you've been really valuable in providing us feedback and information for us to improve the CLIFS database, so we can continuously improve the way we help out the kinase research community. So just a few slides on CLIFS, and I want to take you back to 2011, where CLIFS sort of started. So when I was a PhD student, Oscar van Linden came to me with one small question: could you maybe align all kinase structures for me that are available? So that's a very simple question. And I thought, well, of course I can do it. But then it turns out that after actually 2 years, we were still working on it. And we published CLIFS as a data set of all the kinase structures that were then available, and also an analysis of how all these inhibitors that were in these crystal structures were interacting with the kinases, what kind of chemical moieties were available, what pockets were targeted, and more. Then in 2015, we released the first website of CLIFS as an interactive database. And in 2019, after quite a heroic effort from George Kanev, also the atypical kinases were included in the CLIFS database. And the last update was in the 2020-21 Nucleic Acids Research Database edition, where the latest version of CLIFS was published. And not only different publications have been made, but of course also the landscape has changed, because a lot more kinase structures have been published. Where we started out with 1700 crystal structures, we are now almost at 6,000 crystal structures covering more than 310 different kinases. So what is CLIFS? So this is just a very quick overview of the background. So every week, and the CLIFS server goes into the protein data bank and looks for new kinase structures that have been released. So it tries to identify those kinase structures, and then it splits all those structures into the different chains and alternate models that might be available. Each of these models and chains, they're then consistently aligned using a reference structural alignment that we have created. And then after the alignment, we start decomposing these crystal structures. So we take out the protein, we annotate the pocket, but also extract the pocket. We extract the ligand, we extract waters, cofactors, organometallics, and also annotate the sequence of the structure based on the reference sequence alignment. And then the next step is that all this data is integrated into the kinase database, where we have different algorithms to annotate the structures, to do different calculations, and also curate the structures and provide very systematic and consistent presentation of the different structures that allow you to compare across the different structures. So a key element of CLIFS is the CLIFS pocket definition. So back then, when we were looking at those 1700 crystal structures that were available, we looked at what residues are involved in the interactions with the inhibitors. And then we came up with this annotation. So these are 85 residues that define the binding cleft within each kinase within the catalytic domain. So because we have those 85 residues and based on an alignment, that also enables us to do a comparison of different kinases directly to each other, because we're not comparing the uniprot residue numbers anymore, but we have a consistent residue numbering scheme. So we now know, for example, that position 59 in the alpha D helix is also position 59 in the AKT kinase, or the ABL1 kinase, or the MAPK kinases. So that's the CLIFS residue numbering scheme that will return quite often, because these 85 residues make it possible for us to actually compare ligand binding and interaction analysis across all 6,000 crystal structures that we have in the database. So then the next step in CLIFS is that we annotate the interaction. So we take the pocket, the annotated pocket for those 85 residues, and we take the ligand, and then we look at each individual residue. And for each individual residue, we look at 7 different interaction types and look at whether these interactions are available between the ligand and that residue or not. So for example, within the hinged region, so for hinge 48 in complex with dasatinib, we see that there is a carbon-carbon contact, so that's annotated as either apolar or hydrophobic. We don't have any aromatic interactions in that section, but we do have a hydrogen bond donor acceptor motif, and vice versa, also an acceptor donor motif. So that's also one of these characteristic hinge binding patterns, of course, that we see here. Then the final 2 interactions are the ionic interactions between the residue and the ligand, which are not present in this case. So that means that for each residue, each of the 85 residues in the pocket, we annotate 7 ones and zeros, and that means whether these interactions are present in the complex or not. And we call that the interaction fingerprint, or IFP. One thing that we try to make sure of is that we also curate the atom typing, because if we just interpret the PDB as is, which is an atom position only format, still the bond types have to be interpreted, and often that also leads to issues with the atom typing. And if the atom typing is not correct, of course, that also means that the interactions are not properly registered. So that's a final curation step that we're doing. After this step, we have a set of different pockets that we annotate, whether a ligand targets, for example, the front pocket, the gate area, or the back area, and that I'll come back to later. And also there are different smaller sub-pockets that are three-dimensionally placed, that you can read more about in the publications. And the second step is to also annotate different water clusters that are conserved within the kinase structures. So if you overlay all the 6,000 kinase structures, then you get quite clear clusters of where the waters are conserved in the crystal structures. And we've all given them a name or a number, and that way we can also compare even waters and water interactions across these structures. And because, of course, we're not only looking at the kinases and the kinase inhibitor interaction themselves, we're also looking at the structures. So, for example, this is an example that I've used a couple of times. This is EGFR based on a set of different crystal structures. And you can see that actually there are quite some changes within the kinase structure. But although you would maybe say this is based on MD simulation, this is purely based on different snapshots from crystal structures. And what we annotate from the kinase side is what the conformation is of the P loop, what the conformation is of the alpha C helix, and also of the DFG motif. And one thing that I would like to highlight is annotation of the G-rich loop or the P loop. And that's namely whether we have a closed G-rich loop or an open G-rich loop, and also how the loop itself is oriented. So to that end, we've developed two metrics. So we have the rotation of the loop itself. So that means into which direction the loop is rotated. And then we have two additional metrics. That's namely the G-rich loop angle. So that's the angle from the catalytic loop to the hinge to the G-rich loop, and the distance, which is this distance from the catalytic loop to the G-rich loop. So with that, you can actually capture the rotation of the loop, whether it's open or closed, and also the distance between them. And if we map this for the different structures out there, we see that, for example, in the closed loop that we have here, the loop itself is rotated, but it's quite close to the catalytic loop. So the distance is quite small and the angle is quite small, but it is rotated quite a bit. And here, on the other hand, we have an open G-rich loop, which is not really rotated that much. So there we get a very different pattern. So also in this graph, you can clearly see that these kinase structures are actually quite dynamic. Before I go into the demonstration and also the workshop part across the website, I just want to highlight a few parts of the roadmap that we've been working on. So we're working on a kinase profile that can interpret experimental kinase profiles and then try to explain where this ligand selectivity is coming from. We're working also on interactive sequence alignment and kinase inhibitor miner. We've recently finished a new additional coloring scheme for the website that's a bit more colorblind friendly, this palette, or maybe easier on the eyes in general. And in the back, we're also improving this tautomer and proteination handling. That's also has a bit to do with the atom typing, and we're also refining based on the new structures that we have, and also the AlphaFold efforts in the full reference alignment that we have, and also we're trying to expand the residue numbering to the full kinase. And a while ago, we've implemented new DFG classifiers and also alpha C classifiers. And we're working on the hydrophobic spine annotations. So those are things still to come. So then let's go to the CLIFS website and show you some tips and tricks. So you can easily find it at clifs.net, and let's just dive into it. So when you're coming to the CLIFS website, you're presented with this first page. Of course, we have a cookie banner that you can quickly discard. And on this front page, we have an introduction text, some statistics about what's currently in the CLIFS database. So we have more than 314 different kinases that are covered right now. We're still 8 structures away from the 6,000 milestone, but probably next week we're at 6,000 structures. And when we're splitting all these structures into the different alternate models and chains, we're almost at 12,000 or 13,000 different individual structures. We're covering approximately a small 4,000 different unique inhibitors. And also the user base is continuously growing, and that's very nice to see. Here at the bottom, we have some news corners. So also this workshop is mentioned there, for example, and you can easily read more. And as I mentioned, every week, the CLIFS goes into the protein data bank and acquires the latest structures. So these structures are from the PDB release from yesterday. So they've all been integrated, so you can get a quick update of what's new this week in kinase land. Here at the top, we see the current coverage mapped onto the kinome as published by Manning, and then also extended for the atypical kinases. And in green, you see the kinases that for which we have new structures that were released this week. At the top, we have the menu system, so you can easily browse just all the structures in the CLIFS database. It is a bit heavy and information dense, so it might not be the best way of doing things, but it is possible. We have the search page. We have a page dedicated to drugs and kinase inhibitors in clinical trials. The favorites page to keep track of your favorite kinase structures, and also some additional information. For example, the frequently asked questions, and some more things we're getting to later. At the top right, we have the quick search page. Input box. So here you can, for example, search for a specific PDB code. For if I want to look for a PDB code 1 ATP, for example, it will give you hit 1 ATP, and that can directly take you to the results page. Or I can look, for example, for a specific kinase. So if I'm looking for Bruton tyrosine kinases, I can either search for Bruton or BTK, and it will try to find what you're typing in the HDNC nomenclature. So that's the gene names, or the Manning original nomenclature that's being used here. And that will then give you an overview of all structures available for that specific kinase. And finally, you can also search for specific ligands. So if you know the PDB code for your ligand, so for example, STU for staurosporine, you can also quickly find all structures with staurosporine. So an alternative way, if you really know your way around across the kinome, is just to find your kinase of interest and then click on it, and then you're also immediately taken to the page for that specific kinase via this kinome tree. But I'm going to start off with the results for staurosporin. So I'm searching for STU, which is the 3-letter PDB code for staurosporin, and I'm searching for all of them. So then at the results page, we get 144 entries. So those are the unique models and chains, and these are obtained from 71 different protein database structures. And so here we have an overview of what kinases the structures are from, what kinase family and what kinase group, the PDB code, and also the chain and the model code for that specific entry. And if you're hovering over the ligand, you also get a 2D depiction of that specific ligand, the organism. And if you just want to have an aligned download of that specific complex, you can just quickly click here and you get a mol2 file that's been processed by KLIFS in the aligned format. When we're going down, we see we have a few additional buttons at the bottom. So you can, for example, show the kinome and see how it's distributed. Well, we know that staurosporin is a very promiscuous inhibitor, and that's also very apparent from this view, because we have TK kinases with staurosporin TKL, and even we have atypical kinase inhibitors with staurosporin connected here. So the PI3K gamma is also has been crystallized in complex with staurosporin. So that already gives you a nice overview of where you can actually find staurosporin. If you want more information just from this overview, you can download this overview as an Excel file or as a CSV file. And if you just directly want to obtain all the processed structures, you can click here and download the structures in either a zip file containing the PDB files that have been processed in individual sets. So we have the aligned complex, we have the protein, we have the ligand, the pocket. It's also available as a mol2 file. Or if you're working with MOE, it can also be downloaded as an MOE database that you can directly then plug into MOE. We have two different options. So if it's a smaller download below 100 different structures, then the download will be ready directly and you don't have to provide an email. But larger downloads can take quite a bit of time. So that's why we ask you here to provide your email address, and then you'll be sent a download link via email when it's ready. So this can take a bit of time before you receive the email, but it's being processed in the back just to take care of the server for a bit. Okay, so let's take a look at one of these structures. So let's take a look at the CDK2, for example, and let's take you through the information that's actually available for one of these structures. So we have some general information at the top. So this is a link to the PDB, also the publication from this PDB, when it was released, and the resolution of the crystal structure. The DFG conformation is in the DFG in, and the alpha C conformation is in out. And the salt bridge between the conserved lysine and the conserved glutamate has been broken, and you can see here the distance between their interactive partners, which is very high, so that one has clearly been broken. So then we have some information about the kinase itself, about the annotation of the DFG, the aspartate and the phenylalanine, the activation loop, and also the alpha C helix, and information about the potentially missing residues, missing atoms in the alignment, and the conformation of the G-rich loop that we've just that I've just showed you in the slides. Then here we have a 3D and interactive NGL 3D visualization tool that you can go through. So if I just pause the rocking, you can see that staurosporin is here in the middle, the DFG has been highlighted here in blue. And if you hover over it, you can see the normal residue number complemented with the CLIFS residue number. So the phenylalanine 146 is, for example, the XDFG residue 82 of CLIFS. Then you can also click on the different ligands or on different residues to highlight them. So for example, if we want to show that this residue and this salt bridge is indeed broken, we can click on it and we see that the lysine here is still in its own position, but the alpha C helix is clearly in its out position, and the glutamate has been rotated downward. So this is clearly a broken salt bridge that you can see here, and that then also visually confirms this annotation that the salt bridge has indeed been, is not observed in this structure.
We have a quick question. Can CLIFS be used to filter all ligands that are covalently linked to residues in kinases?
Right now, we don't have that as an option, but we have it on our to-do list. And if you download all the PDBs, then you can, of course, use the connect records to filter out which ones are covalently linked or not. But feel free to also contact me. I can help with that, that effort. But we're planning on actually including this as an option in the search page.
Sounds great.
Yes. So then the next stop are these pocket waters. So in this structure, we only have two conserved waters observed in the kinase pocket. So we have one water here and one there. We don't see any hydrogen bonding pattern with the ligand itself, but we do see that there's a hydrogen bonding with the protein. And that's something that you can use later on as well in the search page to, for example, find a specific water that has been engaged in both hydrogen bonding with the ligand as well as the protein. Then we have some information about the binding pocket sequence. So we have the wild type at the top. And then from the structure, we see that we have a gap here, but that's also in the wild type. But at the end, after the DFG motif at the start of the activation loop, there one of these residues has not been resolved. So that's also clearly visible here. And if there are mutations, they are highlighted in red in this overview. If there are modified residues, so for example, phosphorylate-related residues, they are mentioned in this region. Then we're moving on to the ligand. So we have a quick depiction of staurosporin, a link to search for more structures with staurosporin or to find analogs in CLIFS with staurosporin there. This is an interactive diagram scheme that you can use to visualize this specific structure. And in this case, the structure highlights what residues are in contact with the ligand. So the larger spheres, they are in contact with the ligand, and the color indicates the type of interaction, and that is in line with the coloring that's being used down here at the kinase interaction panel. So we can see that it has an aromatic interaction with the gatekeeper, that's position 45. It has this typical hinge binding pattern, so it has contacts with the hinge. It has a hydrogen bond with two of the hinge binding residues. And this is something that you can also modify for a bit. So if you don't want the CLIFS residue numbering, but you only want to show the residues themselves, or you want to hide, for example, the non-interacting residues, that can provide you with a nice schematic way of looking at a specific structure, or to visualize specific interactions, for example, in the binding cleft. Here
There's a question
pockets.
actually.
Yes.
Can you please repeat how to identify the DFG in and out conformations?
Yeah, so I'll get back to that in a bit. I will discuss that under the search page, because then we have a bit of an additional explanation of how we're doing this annotation actually.
Okay, thanks.
So here we see that Staurosporin doesn't actually engage in any of the very specific subpockets that have been annotated, but it is present in the front part of the cleft. It's not in the gate area, and it's also not in the back area. And of course, mainly DFG out inhibitors are found in the back area, or also type 1.5 inhibitors. Then the key element of CLIFS are the kinase ligand interactions. So here for each individual residue, you see the CLIFS residue numbering. So that's 1 to 85 here at the bottom. You see the number in the crystal structure itself of the residue. And then we have the annotation of the different interactions. So hydrophobic interactions, here's the legend at the top. We have hydrophobic interactions. We saw at the gatekeeper 45 the phenylalanine that has hydrophobic and aromatic interactions. So hydrophobic, and this one means that it's an aromatic face-to-edge interaction with the gatekeeper. And here you can clearly see the interaction with the hinge region. And then we'll get back to the interaction pattern search later. And at the bottom, there's information from Campbell about the bioactivities that are available for this specific ligand. So we have 1,829 different bioactivity records for 404 different kinases. And if we scroll for a bit through this list, we also find the ones that are highlighted, and that's for this specific structure. So this is a CDK2 structure, and also we see that the PIC50 of Staurosporin for CDK2 has been measured 5 times, and it's in a range from 8.4 to 10 with a median of 8.9 as a PIC50, and the PKD is annotated separately. Okay. So then I want to go to the search page, because I think that's the most powerful of this all, because it actually allows you to search for specific kinase structures with the specific patterns and information that you're looking for. So this search page is a very long page, actually. It encompasses quite a lot of different options, but you can actually combine all of these different options. So it's not an exclusive one, so you cannot only, it's not that you can only search for one specific kinase, but you can actually mix and match all these different search options. So it's a good way of defining very specific and also powerful searches. For the kinase classification, that's the simplest form. So here you can search for a specific kinase, and between brackets we have the HDNC nomenclature. You can select the kinase of interest, or you can select the kinase family of interest, or just the whole kinase group. And right now we're annotating human and mouse kinase structures, because those are the 2 biggest ones and the most prevalent in the protein data bank. Then an option that I also quite frequently use, and that's using the substructure searches and the similarity searches. So for example, if I want to search for a specific substructure, I can draw the substructure here. So this is an editor from Molsoft that is free to use, and that's quite convenient. And one small neat little feature is actually this lookup book that's here. So if I want to, for example, look for adenosine, then I can type it in and I immediately get this drawn into the panel. And then I can perform either a substructure search or search for ligands without that substructure, or a similarity search. So let's first try maybe a substructure search. And that should then give us quite some entries, of course, because that also covers ADP and ATP. So those are quite a few. So just a substructure search for adenosine gives us 597 PDB structures. And also, if we look at the kinome, it's a very nice distribution, of course, across both the eukaryotic and the atypical kinases. Going back to the search page, we can also do similarity searches. So for example, if we want to look for sorafenib and we want to identify other ligands that are similar to sorafenib, we can change the type of search to a similarity search. And we have two types of similarity searches. So those are the Morga fingerprints, which are the most frequently used ones, and the Max fingerprints. I mainly use the Morga fingerprints, and then you can set a similarity cutoff. So this would mean a similarity cutoff of 50% more or less, but it's not a one-to-one scale. So 0.5 is actually quite a high similarity. So if I would perform a similarity search here, I get, of course, identical ones. So those are the ones that already have sorafenib in the crystal structure. But then if we scroll down to the bottom, we see that here this similarity is actually decreasing. And then we see that this is still with sorafenib, and then we see some smaller changes. So this is a very quick way to actually identify analogs of a specific inhibitor that you're interested in. And also here, you can download the Excel file. Just want to show you that in this Excel file, we have, again, the information of the different kinases, the different PDBs, chains, species, and in addition, there's the information about the ligand and also allosteric inhibitors if they are present, and also the conformation of the DFG and the alpha C is highlighted here. If you can also download the structures here. In this case, we have a small data set, so you can directly download this. So I'm just going to download here the MOL2 files that are then downloaded. And if we open that up, you get a CSV file that explains, has all the details for each of the different structures that are in the download. So also, again, the orthosteric ligand, allosteric ligand, the quality score, the pocket, the 85 residues according to CLIFS, missing residues, missing atoms, the whole interaction fingerprints. So those are all the 85 residues times the 7 different interaction patterns, and also which subpockets and pockets are targeted by this kinase. And then it's split into different folders. So first we have species, then we have the specific kinase, and then for each specific PDB entry, which has been split into the chains and models, you have the complex, the ligand, the pocket, the protein, waters, and if they are present, also the organometallics. So they've all been split into different segments, and they are all according to the CLIFS alignment. So this is a very quick way of actually collecting an archive of the structures that you're interested in. Then just going back to the search page, we have physical chemical properties. So you can filter on different physical chemical properties of the ligand. So for example, Lipinski, fragment-like properties, lead-like properties, and you can adjust this into any way you want. So if you want to search for smaller molecules with a low heavy atom count, that's very much possible here. Then you can also filter on the different interactions. So if you're interested in those kinase structures in which the gatekeeper, for example, has a hydrogen bond, so that's an H, the legend is at the top again here, you can quickly filter on a specific residue position, so gatekeeper 45, and filter on hydrogen bonds with the gatekeeper. And then we have these main sub-pockets that we also discussed previously. So you have where the ligand is actually in the pocket. So if it targets the front cleft, the gate area, or the back cleft, or maybe all of them. So you can either toggle whether they are present in those areas, yes or no. And also those specific sub-pockets. So those sub-pockets that were also shown here. So that target a specific area, a 3D position in the kinase cleft. Then on the structure, you can filter on the quality score, the release date and the resolution, and whether actually it has a ligand, yes or no. But right now, and I will get back to that for a bit, in a bit, you can also annotate the conformation. I'll get back to that. But I just want to show you that you can also combine this with information from the pocket sequence. So I've just enabled a filter in which the gatekeeper had to be either having a hydrogen bond with the ligand, so that was in position 45. And here I can also define what type of residue the gatekeeper has to be. So for example, I want the gatekeeper to be a threonine that engages in the hydrogen bond with the ligand. And so those are the two filters that I have enabled right now. So if I would search for that, I would now get 205 PDB structures in which those structures have a threonine gatekeeper and a hydrogen bond interaction with the ligand. So let's take a quick look if we can find that also here in the structure. And indeed, if we just zoom in for a bit, we see here we have the gatekeeper here, the threonine, and here we have the ligand that's actually donating to the threonine. So that's a very quick way of identifying specifically those structures in which you engage with a specific interaction with a kinase. So then going back to the search page and the conformations that I promised to talk about. So we recently updated the DFG classifier, and what we are doing right now is we're annotating what way the phenylalanine is rotated and what way the DFG or the aspartate is rotated, and we're also looking at the movement of the catalytic loop itself and the distance between them. The activation loop, of course, I mean. So when you hover here over this question button, you can get more information about this. So if you're only interested in DFG in, out, or out-like structures, you can filter that here. But recently, we've actually added a more powerful function even that you can filter individually on the activation loop distances and also the rotation for the aspartate and the phenylalanine. So for example, if I'm interested in structures in which we have DFG in the in position, but actually a phenylalanine in the out position, so that would mean that both the aspartate and the phenylalanine are pointing inward into the binding site. So that's actually a quite strange conformation. You can select that in this way. When we're searching for this, I haven't tested this this morning, but I'm happy to see that we get some results. So this should actually have one of these strange conformations. So it's classified as outlike, but if we're looking here, we see that actually the phenylalanine has only been partially resolved. And both of the phenylalanine and the DFG are pointing inward instead of towards the alpha C helix.
Okay, you have another question. Can you search for water-mediated interactions?
Yes, yes, we can. Let's take a look. Yeah, just want to quickly finalize here. So here's also all the different options to filter on different conformational states for the different structures. So for example, also the alpha C helix position and the activation loop position and the rotation and the opening of the G-rich loop. Then up to the waters. The waters are here at the bottom. At the waters you find here. So of course you have to know which water is where. But for example, if I move to the drugs page, and I'm gonna quickly just jump over this, I'll get back to that. If we're looking at bosutinib, which is actually known to have this very conserved interaction with a water with its nitrile group. So if we then look at the structure, we see that the bosutinib has this nitrile group here, and that's pointing towards this water. And in the binding pocket waters, it's annotated that this water in the I5 cluster has both a hydrogen bond with the ligand and with the protein. So that's something that we then can use again. So if we're moving back to the search page, we can go to I5 and then specify we want both a hydrogen bond with the protein and the ligand, or only with the ligand, or just the presence or absence of the water. So if we're filtering for hydrogen bond both, then we will get all those structures in which the ligand is also engaged in the hydrogen bond with that specific water and the protein as well. So I'm just taking the top one here, and you can see here that in this case, we have an amide in the ligand that's connected, interacting with the water, and the water is then again probably interacting here with the backbone of the activation loop. So yes, that's possible. Then to sort of round it off, what you can do, we also last year introduced this drugs page. So this drugs and clinical candidates page is an overview that's partially powered by the PKID from the Bonnet lab. And we have complemented this with over 200 in-house annotations of ligands that are currently in clinical trials. And here you can quite quickly find different ligands, and also whether we have structures available for them. So that's the mark here. And you can then show these structures. So for example, for abemaciclib, you can then identify the structures for that specific drug. We have bioactivity data that's directly linked to Campbell as well. And in case we don't have any information, so for example, for belumosudil, which is a BTK inhibitor that was approved last year, we can do a search, for example, for analogs. And then it uses this similarity approach again. And if we then hover over the ligand, you can see what the similarity is. So on the left, you see belumosudil, and on the right, you see the match of the ligand that's in the crystal structure. So here the largest part of the scaffold is actually available. Only the more solvent exposed tail of belumosudil is not present for this structure. But this should already give you quite a good impression of how this ligand binds, and also a good modeling template, I would say. So then I'm gonna jump to the final part. So here we have some additional information. And I would like to highlight here the web services. So we have two APIs. So the top API is the classical API, and the bottom API is the newer API, which has more API calls and also more extensive API calls. If you click on this, you get an explanation of how the API can be used. And this is according to the Swagger definitions. And Dominique will also show you how this can be used in a programmatic way to integrate this. But just to demonstrate, we have 4 different segments. So we have general information about kinases that you can obtain here. So for example, if I want kinase names, and I just want to try this, and I want all human kinases. So for the species, I'm specifying human, and execute this. It will demonstrate what type of call you need to request and do to CLIFS. So that's this call. And then you will get a nicely formatted JSON format that answer in which the name of the kinases is explained, the G name, the accession code for UniProt, the full name, and also the species, and the CLIFS ID. So if I take the Bruton tyrosine kinases, for example, they have CLIFS ID 473, and that's something that you then can use again for the other calls. So if I want to get a list of ligands that are in complex with the structure, I can use the ligands list call, and under kinase ID, I then provide the kinase ID 473, which is the Bruton tyrosine kinase. And if I then execute this, which programmatically would be this call, then we get an overview of all the ligands that have been crystallized in complex with the BTKs, with the PDB codes, the SMILES, and the INCHI keys. If we want more information about the structures themselves, that's available via these calls, and also all the information about the conformation and the different structures. It is available from these calls at the bottom, and also all drugs are available from here. Yes, I see there's another question. So I see that the question from Katarina is whether the drugs and clinical candidates overview is limited to kinase inhibitors for which the PDB was also deposited, or if it is also for kinase inhibitors for which no structure has been deposited. So if we go back to the drugs page, only the ones with a question mark or with a check mark, a green check mark, they have been known to have a crystal structure. So the ones with an X, for those we have at least the small molecule structure, and that's why they're included, but we don't have a crystal structure. So also for the belumosudil example, this one was approved last year, but we don't have any crystal structures right now. And that's why you can, for example, use this analogs button to identify the structures with analogs. And then to close off with, for the first part, this Swagger UI or the advanced programmer interface has also been used to develop NIME nodes. So I'm not sure if you know about NIME. If you do not, you can find out more information under this CLIFS and NIME tab that takes you to a YouTube website that explains more how to use NIME and how to also install the CLIFS NIME nodes in NIME. So what you then can use is, for example, NIME to generate these different questions, these different workflows. So you can integrate I'm going to reset this here. You have different CLIFS nodes, for example, the ligand overview retriever. This one connects to CLIFS, and if we execute it, it will collect all the ligands that have been observed in any of the CLIFS structures. So that's almost 4,000 different crystal structures. And if we look at the output here, then we have also all the information about this. So the CLIFS ligand ID, the PDB code, the smiles, and the INCHI keys, and more. So, for example, one of these similarity searches is also something that you can do locally on your own machine with NIME. So if I generate these chemical fingerprints, so the ECFP4, and I take, for example, the bellamosudil. I've just pre-drawn bellamosudil here, and also generate the fingerprint for bellamosudil. Then I can quickly calculate a fingerprint similarity between all the kinase ligands that have been collected from CLIFS and bellamosudil, and that then will give me a similarity result. So I've sorted here on the Tanimoto score, and again here we see similar results as what we saw on the website. So we see that again, this hit that was very close to actually bellamosudil, but only the more solvent exposed part was not present from bellamosudil. So this is just a very small example of how you can use CLIFS information directly in your NIME nodes. And after a short break, then Andrea and Dominique will take over, and Dominique will also show you how to integrate indeed from the API into your programs using the OpenCat CLIFS workflow, for example.
There's another question for you.
Yes, let me see. Regarding the mapping of residue indices to their CLIFS names, I see that you have done this via specific PDBs with the attribute X-ray numbering, and the reason why there's not a direct mapping between CLIFS name and the position to the UniProt sequence. Well, the reason is that there's quite a big discrepancy between the wild type numbering and the numbering in the crystal structures. So what we often see is that the sequences that have been used in the crystal structures, especially the ones that are a bit older, tend not to be aligned with the numbering on UniProt. So if we would align directly with the UniProt sequence, then we would actually pinpoint the wrong residues in the structures themselves. So that's why there's no direct mapping between CLIFS and the UniProt sequence, because we're really focusing on the structures that we're processing. So hopefully that clears things up.
Okay, great. All right, thanks.
Okay, so then I think it's time for the quick bio break and stretching the legs.
Yeah. So Bailey, I think you're on there. Do you want to just have a quick word?
Yeah, can everyone hear me? Yeah.
Yeah, no problem.
Perfect. Yeah. So yeah, thanks very much, Albert, for the informative workshop that we've had so far. You know, it's certainly easy to see, you know, even from just the brief introduction, how powerful a tool that this could be. You know, we're looking forward to see where that can go. But yeah, sorry, just to introduce myself, my name is Bailey and I work for Liverpool Chirochem. So we are a chemical technology innovator and we're on a mission to accelerate small molecule drug discovery through expanding access to 3D chemical space. So we're proud to sponsor these series of events and workshops as we understand how essential these open source tools are for the global research community. At LCC, we specialize in using stereo-defined N-heterocycles for use in DEL, fragment-based lead discovery, linkers for heterobifunctionals, and also we have our own free discovery virtual library. So if you've listened to any of that and heard me ramble on for a little bit and you think, oh, you know, that you'd like to find out more about how we could support your projects, then please reach out to us through our website, which is liverpoolchirochem.com, or you can find us on LinkedIn. And I'll let everyone go now, and I hope you all enjoy the rest of the workshop. Thank you very much.
Thank you, Bailey. So we'll see you. Hi, I'm not sure which of you is going next. Is it you, Andrea?
Yes, I'm going next.
Okay.
I just wasn't sure if you're gonna welcome everyone back or if I should start.
I think you've done the welcoming, I think, so we should we should move on, I think.
Okay, well, thanks everyone for listening to our workshop today. I will use the next 10 to 15 minutes to give you a quick overview of the work we do with kinases, the open source work, especially those things that heavily depend on the CLIFS database. So it fits very well to everything Albert already explained to you. Before I do that, I just want to mention that Dominique is going to give you really a hands-on insight into the notebooks. And if you want to follow in time, it would be good to open the notebook in Google Colab, and Dominique will share the link here, and run this first cell because the installation takes, I don't know, 3 or 4 minutes. So you have everything set up once she starts. Okay. And with that, I'm gonna start talking a little bit about our group and what we do there. We work in structural bioinformatics and in silico toxicology, and we do method development and application for questions in computer-aided drug design and predictive toxicology. And we are especially interested in combining structural bioinformatics and cheminformatics using machine learning, and we have a focus on cancer research and kinases. We do believe in open source, and we try to make all our developments available for other researchers. So I want to invite you to have a look at our GitHub page, and I just want to introduce a few things that might be of interest for the audience. We do provide teaching material. One thing I will cover in the next slide is Teach OpenCAD, which is specific for our field, but we also have some notebooks available that give a bit more of a basic introduction to Python programming with focus on artificial intelligence in medicine. Then we do have started a Python library that should support structural bio and cheminformatics tasks, OpenCAD, where we also included OpenCAD CLIFS, which will be covered later. And we do have several machine learning based applications where we build models for activity, property, and toxicity prediction. And you can also have a look at those where we also are interested in how can we augment our data, or how can we get more confidence into models. And you always have code examples available. And then, of course, we have a big chunk of kinase research, which will partly be covered here. One more is the Open Kinome initiative that we do together with John Kodera. So you're also invited to have a look there. Let's start with Teach OpenCAD. It's a teaching platform that covers by now 28 introductory lessons for central cheminformatics and structural bioinformatics topics. So this includes database queries, calculation of chemical properties, compound similarity, ligand-based virtual screening, structural modeling like docking, molecular dynamic simulations, and so on. And the notebooks were actually really conceived as from students for students. So we started developing them in our courses. You can use them in a course, or you can use them for self-studies. And you can use it as a material to solve your own research question. And each notebook is designed in a way that you have a theory and a code part, so that you have everything in one place. You have here a few links, and the slides are also made available on the GitHub repo from the workshop today. So you can also click on everything. And we recently published also in NAR the update of the platform. Feel free to have a look there. And as Albert already mentioned, we do a lot of Python-based programming, but we also made part of the notebooks available in NIME, as he showed in his application. This is a summary of how the notebooks look like. So you have, of course, the title and the authors, then the aim of the tutorial, so what will be covered here. And then you have a theory part where you really get textbook examples of what will be calculated. And then you have the code that is executable on the fly. You always see the results directly below the cell. So it's very easy to follow, and it's very easy also to modify it. And we also have a bit of a discussion and a quiz at the end. And this is all in one place, and each notebook is like one lecture that you can go through. This is an overview of all the topics that we have currently available. In blue, you see you can query Campbell, PDB, CLIFS, or PubChem, for example. Then we have many ligand-based topics. So if you want to filter a set of molecules by ADME properties, unwanted substructures, or if you want to look for similar compounds, virtual screening with machine learning, clustering your molecules, or we also added some more deep learning related topics. And if you move over to the structure-based side, which is the orange part here, we look into pharmacophores, binding sites, protein ligand docking, protein ligand interactions, molecular dynamics simulations, and also how to visualize everything in 3D and interactively. And recently we added a new collection which covers kinases, which is heavily dependent on CLIFS. And this will also be partly covered later by Dominique. So let's move to the kinase part, which is the interest of today's workshop. Albert already gave a great introduction, so I will do this very briefly. We are interested in kinases because they are involved in signal transduction and they cause many diseases. The advantage with kinases is that to a big part they are well studied, and there's a high structural coverage, which brings us back to the question that Albert raised in the beginning of his presentation. How can we use all this data? And there, CLIFS is a very great resource. And then, of course, there are still challenges when you want to develop a new kinase drug, because the drug has to be competitive to ATP. If it binds to the ATP binding site, it needs to be selective, which is not so easy because all kinases bind ATP, so the binding site is very similar. You need the right physicochemical properties, and there's also a lot of intellectual property already covered in kinase research. So with our work, we want to provide tools, computational tools that help you to acquire kinase data, to do virtual screening, to build kinase activity models, to study off-target effects, and also do fragment-based design. So as I mentioned before, Teach OpenCAD is already there, and since we are interested in kinases, very often the guinea pig in our notebook is a kinase. So you see here 4 notebooks that simply based on the name of a kinase or the name of a compound or the UniProt ID allow you to collect all the data available. For example, from the PDB, you can collect all structures available for EGFR, filter them by some properties, align them, and then you can look at them or use them for further research. We can query the CLIFS database and, for example, look for the interaction fingerprints that were introduced earlier that are can, for example, be averaged over all available EGFR structures here. We can go to Campbell and automatically query all bioactivity data available for kinase, which we can use for machine learning model building. And we can also go to PubChem and automatically get, for example, similar compounds to a compound of interest, like here, giftinib. What we can also do is, as I said, then build machine learning models. This is an example where we build random forest, support vector machine, and neural nets for based on the EGFR activity data from Campbell. And you can calculate these RUG curves. And there's another notebook that is actually very long because it covers a lot of details. Here you can, for a given protein structure, here an EGFR structure and a given lead compound, do the whole lead optimization process automatically. So the binding site is calculated on the fly using Proteins Plus. Similar ligands are collected from PubChem. Molecular docking is performed with SMINA. Then the protein ligand interactions are calculated and visualized using CLIP and NGL viewer. And then based on some criteria, you can end up with a compound that is predicted to be more active or better fitting. And this is also based on this EGFR kinase example. Now let's come to a few more applications that are really focused or heavily using the CLIFS information, which for one is OpenCAD CLIFS, which allows us to query the data from CLIFS and convert it directly into a data frame, which is easily usable in a pipeline. Then we have developed a fingerprint to compare kinases based on structural information, which we called KISSIM. And we also looked into other measurements or other possibilities to compare kinases. So using the sequence, using the structure, interaction fingerprints, or profiling data. And lastly, we also built KinFragLib, which is a kinase inhibitor fragment library, where we use all available inhibitor data, the structure of those, divide them based on their location in the binding site, annotated through CLIFS. And then we do like a mix and match procedure to generate new compounds that can then be used for molecular docking. Which will not be covered in detail today, this part. So as I said, first we developed OpenCAD, and OpenCAD CLIFS is part of this module to have Python code available for structural bio and cheminformatics tasks. The modules that are available and of interest here are databases CLIFS, which which can be utilized to query the CLIFS database. This can be done offline or online, and with a simple structure by structure PDB query or so, you can get all the information. So what Albert showed you on the website, you can do here programmatically, and you get the result as a data frame, as a pandas data frame, and you can use that throughout your notebook. And Dominique will show you an example of this later. And then also with regard to structures, we have the pocket module where you can look into subpockets and visualize them in the protein. And we have the superposition module, which allows you to streamline or to use other tools for structural alignment on the fly in Python. Then, as I said, we developed KISSIM, the kinase pocket fingerprint, because we believe or we know that sequence alone is not enough to compare proteins. Often structure is more conserved. So as a complement for the meninkinome tree, we wanted a structure-based tree, so a KISSIM tree. And what we do is we again heavily rely on the CLIFS annotation. So we use the 85 residues in CLIFS, and each residue is described by physical, chemical, and distance properties. And since we do have the alignment, we don't need to superpose the structures because that has all been taken care of by CLIFS. And then the residues are described by their size, hydrogen bonding capacity, charge, aromaticity, aliphaticity, and then solvent exposure and side chain orientation, which you see here on the left. And additionally, we really want to consider the spatial arrangement of the residues. And what we came up with is that we subdivided the pocket into 4 regions: the pocket center, the hinge region, the front pocket, and the DFG region. And then we calculate the distance of the residue to these pocket centers. We also calculate the mean standard deviation and skewness of those distances. And then we combine that to over 1,000-bit long vector, which allows us to compare kinases, which can be used in machine learning applications and so on. And just as a quick teaser, with KISSIM, we can detect non-intuitive off-targets. We, for example, have built this kinome tree based on distances between the kinase structures or the KISSIM fingerprint. The color coding is as the Manning groups, and you see that there's a large overlap, but you also see a few examples here where we have a different kinase in between another group, and they actually are known off targets of inhibitors for other key targets. So this can really guide selectivity or polypharmacology studies. And if you look at it from a different angle and look at profiling data, you see a similar effect. For example, erlotinib was developed to target EGFR. But if you look at profiling data, it actually binds to many other kinases. And the known off-targets are SLK, LOC, and GUC. And they are very distant from a sequence point of view, because this is the TK group and this is EGFR. And with the KISSIM fingerprint, we at least find these two kinases also on the top rank. So this could help in advance to find off targets. And we also compared this to other description of kinases like the CLIFS interaction fingerprint, the sequence alone, or another binding site comparison tool, CytoLine. And you see in the ROC curve that KISSIM really performs quite nicely here. What's also nice in the package that Dominique developed is that you can look at the individual residues and the distances between kinases in 3D and interactively, which can help you to study the differences. And then finally, which will also be covered by Dominique later, is notebooks from our Teach OpenCat Kinase edition, where we wanted to streamline this idea of looking into kinase similarities from different angles. So looking at the sequence, the structure, interactions, and profiling data. And we streamlined this as a pipeline with 6 notebooks. So the first one talks a little bit about kinases in general, and you can define your set of kinases that you want to investigate. And from there on, everything downstream runs completely automatic. So you can calculate the pocket sequences, the KISSIM fingerprints, the interaction fingerprints from CLIFS, and ligand profiles based on Campbell data. And then you can automatically generate a distance matrix between all kinases that you're interested in. And then these nice heat maps and cluster trees are generated. And you can look at the similarity between kinases from these angles, and this can help you to understand off-target effects or to find new points to other targets that might be of interest. And with that, I'm finished with this short introduction, and I invite you to follow Dominique to the hands-on workshop where she will cover the CLIFS-based kinase applications that we provide.
So, hello, this is me. I'll just jump right in. Thanks, Andrea, for this very nice introduction. You should be seeing my Google Colab instance. Wonderful.
That's correct, we do. Just to mention that if anybody has questions, please put them in the Q&A. We'll relay them to the presenter.
Perfect. Okay, so let's do this hands-on section of the workshop, the Python focused part of this. So what we'll do now is we'll take a look at the CLIFS Swagger API or Open API that Albert already showed to you, but this time we'll take a look at how to use it from Python. We'll take a look at the OpenCast CLIFS package, as mentioned several times already, and then we'll have a look at how we can use the CLIFS data for kinase similarity. And in this demo, we'll focus on the CLIFS interaction fingerprints and the KISSIM fingerprints. And yeah, the what I show you here is extracted from this kinase similarity edition on Teach OpenCut, which we developed with Talia Kimba, a PhD student in our group. So for reference, I put all the links here to those notebooks and the resources that we're discussing today. And maybe you have done it already or would like to do it now. With this cell code, you will be able to install Conda Colab, which allows you then to install the Conda package KISM, which includes also other packages that we need for OpenCut CLIFS and so on. So oopsie, I'll start here with some general imports. Wonderful. I'll define a kinase set.
Could you maybe just give people just a 30-second introduction to how you use a Google Colab notebook?
Okay, yes, that is actually a good idea. So can I click here? No, you do not want this. Okay, I'll just do it again. Da-da-da. Shouldn't. Okay, so apparently, oh no, wonderful. So you click on this link that I posted in our chat, and it should bring you right here to this Google Colab instance. And I think it should already be ready for you. So you can run code cells via this button here, or I'm on a Mac, so Command Enter will, it will ask you if you trust it. I do. So that's the way you run code cells here. And I think that is for now everything that you've yeah, wonderful, very nice. So that's for now everything I think you need to know. And if we're doing something else, then I'll comment on it. But yeah, please let me know if you have questions while you follow along. Okay, so the kinase set that we defined it right here. We'll comment on it a little bit later when we get some information from the CLIFS database. And I don't have to say much here because Albert already did quite a lot of it. So I'll just open the Swagger user interface again to say again that we have these 4 segments here, and then different requests that we can send to the CLIFS database with certain parameters that we can set. And the very nice thing, where's my tab, is that CLIFS also offered these REST API scheme as a JSON file here. So in a way, everything that you've seen before, you see here again. The example I showed was kinase similarities, parameters here, the description. So it's all encoded in here. And what you can do is, so you could write like, okay, so you can use these specifications to kind of put together the URLs that you need to ask CLIFS for data. But there are already nice Python packages available that can use these open API definitions and dynamically create a Python package for you. So that's the first thing that I'd like to show. So we have Bravado is one of those nice packages. We import the Swagger client. I said like it used to be called Swagger, and now I think it's called Open API. And we put here the URL to this JSON file and generate a CLIFS client. Ta-da! Give it a moment. And then you already have everything at your fingertips. Let's see if the pop-up windows, can you see them? Can someone not? Or are they not visible? That's one thing that I was wondering.
See them.
Yes, that is excellent. I'm very happy about that. Okay, so you can see exactly what we've looked at in the Swagger URL again here. So let's do information dot, and then the functions come up now that will generate the URL that you need to ask for your data. And we'll do that right now. Next cell. So we want some information for EGFR and human. We'll send the request, we'll get the response from the server and the result of that response. And this is how it would look like as a Python output. We can do the same for another category, for example, structures, and we'd like to get all the structural annotations, for example, these PDBs. And you might recognize it from for example, the CSV file that Albert showed you, which you can download. So you find again all these nice things like the subpockets, are they occupied, the pocket, and so forth. So a lot of information. We'll take a look later more. So the thing is that in our group, we use CLIFS really a lot, and people tended to kind of write the same code over and over again, you know, like these bits, initializing the API, then reformatting the output in a way that it's easier to use for us directly. We work a lot with pandas data frames because it's a quite nice tabular view of these kind of annotations. And that's why we, in the end, said, okay, let's write a Python package, a wrapper around this, and then we'll simply use that, and everyone in the group uses the same code, and maybe it's even useful for others who also want to use the CLIFS database from Python. Andrea already mentioned this here a little bit, the different data types that you can get from CLIFS. You can either use the CLIFS database, as I showed you before with this Bravado axis, or you could also download the CLIFS database, point OpenCut to that folder, and it would allow you to use the exact same API that you would use for the online version, and you get the same formatted pandas data frames out of this, because we used to switch a little bit between online and offline. If we're working with really big data sets, we would download them and work with that. Okay, so let's do it. From OpenCut, CLIFS, the submodule CLIFS, we import the remote setup and initialize a session, and we tell pandas, yeah, please show all the columns that there are with this command. And I just put here a table of the kind of the signature that OpenCut CLIFS is using. So you decide what kind of data you would like to have, and then you say, and I would like to fetch it by certain identifiers. Not all identifiers are available for all data types, but yeah, that's just the way it is at the moment. Genau, so let's see. We'd like to use our CLIFS session to get some information about kinases by the kinase names that we defined at the very beginning. So let's do that. We'll get back a nice pandas data frame. Here are the kinases that we defined at the beginning. Each kinase has a CLIFS identifier. We will use that later. And you get a lot of information on these kinases, for example, the kinase groups. So we chose 2 TK kinases, CMGC and an STE kinase, and then like an outlier, an atypical kinase. Okay, so what I'll do is I'll just save the kinase CLIFS IDs in a list here. Because we will use it later. So this is just some preparation for later. Since we'd like to look at CLIFS interaction fingerprints and KISSIN fingerprints, which both are structure-based, we'd like to fetch now a couple of structures that we'd like to work on in the following. So yeah, this is again our kinase set. We again use our CLIFS session. This time we'd like to fetch structures by kinase name, or we could use the kinase IDs. Doesn't matter in that part. I'm dropping a column. Let's just leave it at that. And let's get a few information about the data that we're getting right here. So for these 5 kinases, we have over 1,000 structures. Genau. And this is what it looks like. I've shown you this before when using the Bravado client. This time it's this data frame, and can go through it again. Maybe here a comment. Also, structures have a CLIFS ID, which we'll use later on. You have here those alternative models and chains. Albert introduced that very nicely. You have information about kinases. Some you will see here, some columns have none values because that kind of data is only available when you get it from the CLIFS download. But using the API here, you could get the kinases when you put kinases here. Genau, and a lot of other conformational data and so on. I'd like to filter structures now a little bit. So we'd like to focus on human DFGN human structures in DFGN conformation with a high resolution and a high quality score. Quality score kind of gives you an idea on how good the alignment was, how also if there are only few missing residues or atoms, and so on. So let's the higher the better. So let's say greater than or equal to 6, and we'd like structure bound ligand bound structures because we want to work with interaction fingerprints. So let's align this between the interaction fingerprints and KISM. Okay, so in pandas, you can filter the data frame according to the criteria above like this. And I'll just get a few statistics, like just the number of structures that are remaining. And in this case, over 500. Let's just count how many structures we have per kinase. If GFR is a popular or a very well studied kinase, so we have a lot there. I'm doing now a little, it's not a hack, but I'm making my life a bit easier in reducing the number of structures to save a bit of computing time here. I wouldn't necessarily do that if I did that for research, but we're doing it right now here. So I'll just sort the structures again a little bit to get the best structures on top per kinase based on resolution and quality score. And then I'm grouping my data frame by the kinases that we have, and I just keep the best 3, and then I need to execute this part, and then he knows what to do. Okay, so this time we have 3 kinases, 3 structures per kinase. Wonderful. And again, I'm just preparing. I'll save the structure CLIFS IDs in this variable here. Okay, let's transition into the kinase similarity part, which will still use OpenCut CLIFS in some examples. I don't have to say anything really about the interaction fingerprint. 85 residues and 7 features per residue, and we'll just fetch it. So we're using our session again. This time we'd like interactions. We're using the structure CLIFS IDs, and then we'll just take a look at how this data frame looks like. So here are our structures, and here are our interaction fingerprints. What I would like now is to have a bit more information about the structure, like more than the ID. So I'm simply merging my interaction fingerprint data frame with the structures data frame that we already have. And I'll show you again how this looks like. Okay, so you will recognize this bit from before and this bit from much before. So wonderful. Okay. We have now our interaction fingerprints. What we'd like to do now is compare them to each other in all against all comparison. And we would like to use this scikit-learn function to do that. And we'd like to have this as Jacquard distances, since we have a binary fingerprint here. In order to use this function, we need to, let's say, transform or format this fingerprint in a different way. We need a kind of a list of trues and falses instead of zeros and ones. So this is what I'll do now. It's just a bit code here right now. So I'm reformatting this data frame into a series with, I'm keeping these two pieces of information, like what structure ID is that and which kinase is it. And then I'm just transforming this string into this Boolean list. A bit more housekeeping. I'm just keeping track of these two index lists here for later usage. Just an example, the kinases here will be stored in this pandas index. And I'm getting this section here as an array because scikit-learn wants to have an array. Okay, so we are ready now. We can use the scikit-learn function, put in the array. I'll show you the shape of the resulting distance matrix. 15 times 15 makes sense. We had 3 structures for 5 kinases. And yeah, since we do love pandas data frames, we'll put it back in a data frame. So this is the array, and the index and the columns will be our structure CLIFS IDs, which we kept before. I don't know if that's a word, but I made it up now. Okay, so in the end, we have this 15 times 15 structure distance matrix. But what we are really interested in is the kinase matrix, right? So at the moment, we have multiple structure pairs which describe the same kinase pair, and we'd like to extract kind of one representative structure pair per kinase pair. And we decided to say we will choose the most similar structures to each other as that representative. So a bit more just technical detail. So I'm copying our structure distance matrix, and I'm replacing now the columns and rows names with the kinase names as a pre-step for what we're doing next. So we see here these 9 distances kind of describe the same kinase pair. It's a bit boring here at this point because it's the same kinase, and we'll choose the minimum of those. So in this case, the same kinase has a distance of 0, so they are identical. A bit of pandas workaround. We unstack the matrix so that we kind of have per row 1 pair. We group then this data frame by kinase pairs. We take the minimum distance that we can find, and then we unstack it back into a matrix. I do note that you can certainly also do this differently, for example, only using NumPy. Okay, so our structure matrix is 15s times 15s, and we reduced it now to this 5 times 5 matrix, and I'll show it to you right here. Ta-da, there we are. This is what we want, and we can style pandas data frames very nicely. I like to do that. So we have a bit of color, and for EGFR, for example, we have now app B2 as the most similar kinase, which makes sense. They belong to the same family, the EGFR family. Okay, so first part. Second part is the kiss and fingerprint. It will be quicker because we have a Python package that does a lot of the work that I showed you now step by step under the hood, so to say. A quick recap. The kiss and fingerprint is fundamentally based on the CLIFS binding site alignment and annotation. So we have these 85 CLIFS pocket residues, and each of those residues we encode physicochemically and spatially. And let's jump right into this. So the KISM API looks as follows. So we import the KISM encoding submodule, and we want this fingerprint generator class. You can also encode a single fingerprints. That would be simply this. But we have more. So we import this, and I'd like to show you the signature. This is quite nice in Google Colab. It will show you the documentation of functions in this help window. Let me look at the time. Wonderful. Okay. So we have here as parameters, we want structure CLIFS IDs. So KISM really works with those IDs. So if you don't have them, you would first use, for example, OpenCut CLIFS to retrieve those IDs. And I'm just reading something in the chat. Yes, thank you. Yes, I recommend not doing that for now. Like you can, okay, you can do it. The thing is, I'll show you later an NGL view widget. And I saw that on Google Colab, the coloring is not quite right. So I'll switch to Jupyter Lab, but feel free to include this third-party widgets so that at least you can see something, although it's not perfect. Getting there in a bit. Okay, so we're offering here to pass a CLIFS session. If you don't do it, it will just set up this remote session with OpenCut CLIFS. But as I said, sometimes you would like to work with your local data with the local CLIFS download, and you could here then set the path. And if you're working with a lot of structures, then you might want to use several cores because it does take a bit of time. So speaking of a bit of time, on Google Colab, I saw that it takes longer than on on Jupyter Lab, for example. I don't know why, but I'll just comment in the meanwhile that it is possible for you to store the fingerprints with these utility functions here. And also, I mean, if you can save it, you can load it. And in the meantime, while this is doing its magic, I thought I'd do point out to maybe the GitHub, the GitHub KISM repository, which is linking to our documentation, which has much more detail on how to use this package. So there is an encoding section for either one structure or multiple structures. That's what we did. There is the comparison module that we'll look at in a tiny bit. And yeah, here I'd like to also point out that all the features that we are using, you can use them yourself for something that you are interested in. And in this documentation, you can go through these different features bit by bit and see how they are working and how you could use them individually. Okay, so let's take a look. If you're not ready, I have a backup. So if it's not like ready for you, so it took here 2.5 minutes for some reason. I put in a little hack, so you can download this JSON file, which would be produced here, and then load it. Apparently, Google Colab loads it to this location. Let's see. So I put the commands in here. Do you want me to download it first? So you first have to stop this. Otherwise, it's waiting. Then you can remove output, which is very nice. Let's just download it again. So in your case, it would be a copy paste of these code lines. If you click here, you can create new cells, a code cell, for example, and here you could copy and paste stuff in. So it was downloaded, it was loaded. So this would actually be, this fingerprint generator would be the output of this one. Let's move on in the interest of time. Then the data attribute contains then all these different fingerprints. So as a key, you have the structure CLIFS ID and then the different fingerprints as values. I'll just, for some examples, I'll just save some example IDs and the respective example kinases. So we'll have an example for EGFR and P38A. And I will use this to load this fingerprint for this example EGFR structure. And you can access, let's go back again to have this nice pop-up windows. So you can access now the physical chemical properties here, the spatial, oh yeah, that doesn't work here, I don't know why. Spatial property distances, it's called, the different subpockets here and so forth. So you can investigate it a little bit, just showing you it's really there. Afterwards, you will notice these are not normalized. Also the physical chemical properties are not normalized, which we will fix right now. Not fix, but we'd like to have them normalized for our comparison later. So we'll import this class. We can again have a look at the documentation here. It takes as input a fingerprint generator, and we'll do a min-max normalization based on min-max values that we inferred from the data set that we've been using. And it does it really per position. If you do fine grade, it does it for example, the distance features per subpocket, really, and subpocket and residue. Okay, let's move on. In the interest of time, I'm showing you again. It's a similar setup, and I'm showing you again an example for these normalized physical-chemical properties now. Okay. We have encoded our fingerprints, we've normalized them, let's compare them, and this will be quite quick. So we have a fingerprint distance generator here. It will take our normalized fingerprint generator, and again in this distance, in this data attribute, we have now all the pairwise distances. So between the structures, we have annotated which kind of kinases they belong to, and then the distances here and a bit coverage, because not all bits in the KISM fingerprint can be calculated. For example, in case a residue is simply missing, then we can't do anything about it. Okay, then we have this utility thing here to get the kinase matrix out of this. Ta-da! And then you remember the styling of data frames, which I like so much. So again, these two are the most similar. And I will skip this part and show you directly this. And I'm going here to show it to you. So we have in KISM a viewer module, which allows you to take a look at the difference between a structure pair that you are interested in. And it maps kind of the difference between the respective bits for the different features here. And the idea would be to use such a visualization to find out which bits in the binding pocket could be of interest to modify your ligand to make it more selective, for example, and prevent from one of the kinases to be an off target at the end of your campaign. Okay, I'm almost at the end. I'd just like to mentioned two more plotting options that we show on teach-up and cut. So we defined two functions here, a heat map and a dendrogram, which allows you to compare this. So I'm not in my Jupyter, my Colab anymore. Let's do that properly here. Zack. The heat map and the dendrogram, ta-da, uses here SciPy to visualize the dendrogram. I'm just putting our two kinase distance matrices into this dictionary, just for cosmetics here. And what we'll do now is we'll just plot the heat map and the dendrogram side by side for these two versions. Zack. And let's maybe take a look at the dendrogram down here. Andrea already mentioned that with the kiss and fingerprint, we do have this similarity to EGFR of this SLK kinase, which is like sequence-based far away from EGFR, but has been shown in profiling data to be affected by allotinib, all those three. Okay, and in both cases, you nicely see here that the atypical kinase is far away from them. I'd like to circle back to teach-up and cut just to show you. This is the kinase similarity edition that we have. We covered today parts of this notebook and this notebook. We also, both of them using CLIFS, right? We also look at sequence similarity and identity using the CLIFS pocket sequence. And Andrea already mentioned the ligand profiling as well. And then we have this nice notebook that brings together everything. And then you can have these different perspectives side by side. And with that, I think I should stop and say thank you.
So that was really wonderful, really was. I think it really underlines the importance of having these open source resources, the way that other people can build on them.
Yes, you could even, if you had another perspective that you are interested in, you could try and use the setup that we were, because it's quite parallel, the setup of those notebooks. You could put your perspective in there and rerun this notebook with a fifth column. So that's like our dream case of this, you know, for the future. Oh.
So, some very nice comments in the chat, which is always nice to see. I think the other thing that you've perhaps inadvertently underlined is that Python is becoming a key tool for all chemists, structural biologists, etc. And that maybe you know, undergraduate courses are going to have to include Python programming as part of the key part of the course.
Yeah, I agree with that. And I think that people are moving towards that.
Yeah. Yeah, certainly one of the things that we've been asked to produce is a Python programming course for chemists, and I think we're slowly putting things together, but it would be I think some of these things would be perfect material for that. Yeah. Cool. Okay. Well, it just remains for me to thank all three of you for actually a wonderful 2 hours. It's been really top-class science, and it's just fantastic to see all these resources available for everybody to use. So I suggest you go and have a nice cup of tea or something stronger now, and enjoy the rest of your evening. Once again, thanks very much.
Thank you, and thanks for the invitation.
Okay.
Thanks so much for having us.
Yeah. It's great.
Thank
so
you.
I'll edit the video over the next couple of days, and next week it'll be on the CICAG YouTube channel. Great. Okay. Thanks very much. Bye.
Thank you. Bye.
Bye.
Bye.